Today we're going to introduce features of polynomials. Please make note of the key vocabulary. These are all terms that you should already be familiar with or will become familiar with over the next couple of days. Let's start with the form of a polynomial expression. A polynomial expression will follow this basic form outlined here, where we have something like a times x to the power of n and multiple terms. The letters in front, a, b, c, d, are our coefficients. The exponents, for example, x to the power of n, x to the power of n minus 1, are usually written in descending form, but it may not include every power. So for example, if we have x to the power of 4, it might jump down to the x to the power of 2 without having x to the power of 3. In order to be a proper polynomial, our exponents must be whole numbers, our coefficients must be real numbers. So those can include fractions, decimals, radicals, and that's fine. When we look at a polynomial, one of the things we can identify is the degree. The polynomial's degree is determined by exponent, specifically by the highest. So we'll call that n, and that is our highest power of x. Highest power of x. The leading coefficient for a polynomial will be the coefficient for that leading term. So for our example, a is the leading coefficient. It is the coefficient, I'm going to shorten that, coefficient of the highest power of x. Let's look at some example polynomials and let's just practice finding the degree and the leading coefficient. So we'll take a look at example 1. And let's start by looking for the term that has the highest power on x. For f of x, that is 5x to the power of 4. That gives us a degree of 4 based off the power on the x and a leading coefficient of 5. If we want to name this, when we have something to the power of 4, we usually just use the general term polynomial. Going on, we can fill in the rest of them the same way. The next one is a degree of 3. It sometimes throws people off that there is a root 5 in front, but remember your coefficient can be any real number, so that's actually okay. Our leading coefficient is root 5, and we would call this one a cubic because the highest power is x to the power of 3. Same idea for the next one, degree of 2, leading coefficient negative 3. This is a quadratic. The next one is not in order, so make sure you're looking for the highest power. We have negative 3 plus 4x, but we look at the term with the highest power, so we have a degree of 1, because remember there is an exponent of 1 that we don't always write out, and a leading coefficient of 4. This is linear. Our last polynomial does not have an x anywhere, but this is where it helps to remember that you can think of a constant as negative 3 times x to the power of 0, because x to the power of 0 is just 1. So this is actually a degree 0. It does not really have a leading coefficient. I would call that number 3 the constant. So negative 3 is your constant instead of a coefficient. And we call it a constant function. The shape of a polynomial is such that polynomials are continuous. And by continuous, we mean it is no breaks, no sharp corners. If we look at these examples, let's decide what would be considered a polynomial. The first one is linear and obviously a polynomial, so we'll say yes. The next one also has no breaks, no sharp corners, so yes for the quadratic, yes for the cubic. The last one has a break, so as much as part of it is continuous and another part is continuous, there is that one area where it is not attached, and therefore it is not a polynomial. The next thing we're going to look at is end behavior of polynomial functions. And to do this, we're going to look at several features for linear, quadratic, and cubic functions. Let's do one of these together, and then you can fill in similar answers for the rest. So let's take a look at the basic case of y equals x. And let's just sketch a quick graph of that. Hopefully we're able to sketch one pretty quickly and know what that looks like at this point. So we have a straight line, and we're going to start by discussing the end behavior. The end behavior is what direction does the graph go in at either end. To the right, our graph is going up. To the left, our graph is going down, and those are the two cases that we're looking for, up or down. We discuss both to the right and to the left. We'll do our domain and range just in a shorter form. We won't worry about set notation because we don't have a lot of space. Our domain is all real numbers. Our range is all real numbers. The last thing we want to consider is if our polynomial was in the form a times x to the power of n, can we identify n and a? N is the degree coming from our exponent. This is a degree 1. It's worth noting that is an odd degree, and it would be helpful to note for the rest of them, is it even or odd? Our a value in this case is 1, but in general, can we just discuss is a greater than 0 or less than 0, positive or negative? A is greater than 0. Let's actually do the last one. Let's look at the negative cubic, and then you can fill in the rest yourself. So we're going to follow the same things, end behavior, domain, range, n, and a. But let's come all the way across to the negative x cubed. Now to sketch this one, you can do a little table of values if you need to, but we're really only going to be able to fit 3 points on here, and then hopefully we kind of remember the basic shape of a cubic. All right, starting with end behavior. This graph goes down to the right, but up to the left. The domain is still all real numbers. The range is all real numbers. The degree is 3. Again, worth noting that is an odd degree. And a is less than 0. Now that we've filled those in, can you take a minute to pause the video and fill in similar information for the other 4 graphs in the middle? When you unpause, I'll have the answers here. There we go. Take a minute to compare your graphs and see if there's anything you need to correct. Now, hopefully we notice a little bit of a pattern once we've filled all of these in, particularly with our end behavior and also with the basic shape of the graph. In general, n determines the basic shape of the graph. So for example, having an n value of 1 or an exponent of 1 tells us it will be linear, an exponent of 2 tells us the graph is quadratic, and so on. A determines what way is going to be positive and what way is going to be negative. So for example, when we have our original linear graph, the end behavior, it goes up to the right and down to the left. As soon as we have a negative in front of the x, so essentially we're multiplying the function by -1, it does the opposite. It goes down to the right, up to the left. Notice how it's affecting the y values. This is essentially a vertical reflection. That's what the negative sign in front does, remember? So because of that, A will determine our end behavior. The tip I usually give for this is look at the right side of the graph. I'll put that into tip. Look at right side of graph. So notice that for all of our positive functions, the graph goes up to the right. When we have a negative function, the graph goes down to the right. The end behavior on the left may change. Notice that with an odd degree, it does the opposite. So if we take a look at, let's look at the x cubed. It goes up to the right and down to the left. The same thing happens with y equals x, up to the right, down to the left. That will happen for any odd degree. On the flip side, if we have an even degree, if it goes up to the right, notice how it also goes up to the left. If it goes down to the right, it goes down to the left. That is what the degree determines. All right, going on to our next concept. Our next concept is turning points. Turning points are anywhere where the graph changes direction. They are generated by the middle terms of the polynomial function. If we have a function with a degree of n, think about the maximum number of turning points. For example, coming back to our quadratic where we have y equals x squared, it has a degree of 2. The maximum number of turning points in a quadratic is 1. Our basic cubic doesn't really show a turning point. It rather shows a flattened inflection point. But if you have cubics with middle terms, they can have turning points, and the maximum they can have is 2. The general formula for that is if the degree is n, the maximum number of turning points is n minus 1. It could also be fewer. So you notice in the case of our y equals x cubed, it is fewer. Let's look at an example of this. So we'll take an unknown polynomial function, for example 2, and let's start by counting how many turning points are there. We have 1 over here, 1 over here, 1 over here, 1 over here. We have 4 turning points. That tells us, for example, we know this is not a cubic because a cubic has a maximum of 2. If something had a degree of 4, it would have a maximum of 3 turning points. This, because it has 4 turning points, must be at least degree 5. It could be a higher degree function that just has less turning points, but we know the minimum degree. So we can say the polynomial must be at least degree 5. All right, let's take a look at a couple examples of equations this time, and we'll decide the same thing for the function. We'll determine the degree. We'll also identify our end behavior, and then we'll decide the maximum number of turning points. So without graphing, we don't know the exact number, but we can determine what the maximum is based off the degree. Let's come in on example 1, and we start just by looking at our leading term, the one with the highest power. We have negative 5 x to the power of 5. The first thing that's probably easiest to identify is our degree. Our degree is 5. What does this tell us about the end behavior of the graph? Well, we're also going to need to look at our a value, I think. A is equal to negative 5. So looking at the degree, we have an odd degree, which means one behavior will be going up, one behavior will be going down. You can think of that as the arrows are opposite, one up, one down. All right, arrows opposite. Normally, for a positive function, we would be going up to the right. Because we have a negative a value, we should actually be going down to the right. So our end behavior is down to the right. And because we have an odd function with one part going up and one part going down, we know we're also going up to the left. Okay, we also know that we have a maximum of 4 turning points for a degree 5 function. Let's do that one more time. Okay, looking at B, again, let's start with our leading term. Now this leading term does have a coefficient with a negative exponent. That's okay. Remember, we allow all real numbers. That includes fractional exponents. That's fine. Don't let that exponent confuse you. We are still using the exponent on the x for our degree. So our degree is equal to 8. Notice that is an even degree. So if you think about your end behavior at the left and the right, it should be in the same direction, either both up or both down. I will say the arrows are in the same direction. Next, we look at our a value. A is equal to 2 to the power of negative 3. Remember that a negative exponent actually just means you can write it as 1 over. This is equivalent to 1 over 8. So that is a positive a value. Positive a value means our graph normally goes up to the right, and that is exactly what will happen for our end behavior here. So end behavior. The graph will be going up to the right. And because it is an even graph and the arrows are in the same direction, it will also be going up to the left. All right, the final thing we can find is the maximum number of turning points. For a function of degree 8, that is a maximum of 7 turning points. It may have less than 7, but the most it could possibly have is 7. All right, that's everything for day 1.